Alright, good morning J2s. I'll be going through question 4 on prelim paper 3 on solubility equilibrium as well as periodic table questions. Okay, so 4C part 1, using table 4.1, calculate the solubility of iron 2 phosphate. So just a very quick recap on what solubility is. It is actually the maximum amount or the mass of a substance that will dissolve in a given solvent at a specific temperature. What essentially it really means, right, is that how much of the substance can be dissolved. If let's say I have 100 cm of the solvent at a fixed temperature, okay, what's the maximum mass or the maximum number of moles in that volume? So solubility, we are looking at mole per dm cube, which is concentration of the substance that can be dissolved, right? Whereas for KSP, it is actually an equilibrium constant that relates to the solubility of the sparingly soluble salt. We have KSP equivalent to the ions that's involved to the power, to its power, and units of KSP is mole per dm cube to the relevant power. So how do we approach this question? To find the solubility of iron 2 phosphate, you let it be X. And since in the table it is given that KSP of iron 2 sulfate is 1.07 times 10 to the power of negative 29, first form this particular equation, alright, where you have iron 2 phosphate, okay, in equilibrium with its ions. So know that there should be 3 Fe2 plus aqueous and 2 of phosphate ions. And with that, form the KSP expression. Now, please be very careful because a lot of you will actually make mistakes over here. Whether is it coefficient or the powers. Okay, so this is 3x to the power of 3 multiplied by 2x to the power of 2. So guys, you have to please take note of the powers. Alright. In the end, you should get 108x to the power of 5, not 6x to the power of 5. Because there are so many of you that just take 3 multiplied by 2. So in the end, you get 6x to the power of 5 equals to 1.07. That's wrong. Or some of you just miss out the coefficient directly. Just take x to the power of 5 equals to this. That's wrong as well. Okay, please take note. These are the common mistakes. So your coefficient, please multiply by the power accordingly. Okay, so in the end, you should get that solubility of iron 2 phosphate to be 6.3 times 10 to the power of negative 7 mole per dm cube. That'll give you that 1 mark. So common mistakes, like I mentioned earlier on, is calculation errors or pressing of the calculator. So please go and practice. How do you get x if let's say your powers is x to the power of 5? Alright? Another thing is that a lot of you actually read the question wrongly. You calculate the solubility of iron 2 sulfide instead. There are 3 KSP given. You have selected the wrong one, okay, to approach this question. So please take note. Alright, so for question 4C part 2, you are given a solid iron 2 nitrate. It is added into a solution that is containing 0.150 mole per dm cube of sodium sulfide over here, as well as 0.2 mole per dm cube of sodium hydroxide. That means both the sulfide ions and the hydroxide ions exist as a mixture over here. Then you slowly add in the solid iron 2 nitrate, right? So based on the table given to you, you have to think about it. That means once the solid, so the thought process should be both iron 2 sulfide as well as iron 2 hydroxide, they are sparingly soluble salts. What does it mean? That means that PPT can be formed once you have iron 2 with sulfide together, at the same time iron 2 with hydroxides together. So the addition of this solid introduces Fe2 plus into the solution because it gets dissolved in the solution, right? So the hint to this question, they ask you to calculate the concentration of sulfide ions remaining in the solution when iron 2 hydroxide starts to precipitate. There's a big hint over here. Without even calculating, okay, the solubility of the salt, you can already know from the question context that S2 minus sulfide ions remaining in the solution. So this means that the IP, the ionic product of iron 2 sulfide, it reaches KSP first and it starts to precipitate first. Okay, once it starts to precipitate, then you'll know how much of the S2 minus is actually remaining in the solution. Okay, so from here, to solve this question, you have to find the concentration of Fe2 plus when iron 2 hydroxide reaches KSP. After that, using this concentration of Fe2 plus, find the S2 minus concentration of sulfide that's remaining in the solution. Because iron 2 sulfate is still in equilibrium with its aqueous ions, solution is still saturated. Okay, firstly, from the hint, you know that iron 2 sulfide reaches KSP first. The ionic product reaches KSP first. So it starts to precipitate, right? So this question is essentially asking, how much of sulfide will remain in the solution when iron 2 hydroxide starts to precipitate? When the ionic product actually reaches KSP of iron 2 hydroxide. Why will it reach the KSP of iron 2 hydroxide? It is because we continue to dissolve more of the iron 2 nitrate inside the solution. Alright? So at this point, when iron 2 hydroxide starts to precipitate, don't forget, iron 2 sulfide is still in saturation, right? Which is why iron 2 sulfide is still in equilibrium with its aqueous ions. Solution is still saturated. IP is still equals to KSP of iron sulfide. So let's take a look at the solution that's given to you. So first thing, IP equals to KSP when iron 2 hydroxide precipitate. First find Fe2 plus. Alright? So based on the solution given to you, taking the KSP of iron 2 hydroxide and equate it to the concentration of OH minus that's involved. Okay, in the end you'll get Fe2 plus is this. Once you have that, to find the concentration of S2 minus that's present, that still remain in the solution, you take the KSP of FeS, equate it to the concentration of Fe2 plus at that moment, okay, and multiply it by S2 minus. Then you have this 4.93 times 10 to the power of negative 3. So common mistakes is this. Some people actually use the KSP of iron 2 sulfide to find the concentration of Fe2 plus and use it to account for the Fe2 plus that's present when when iron 2 sulfate starts to precipitate. And this was your answer. So that's not correct, yeah? And some of you actually equate 0.150 minus what you have here, 4.93 times 10 to the power of negative 3. You minus it off such that you find the concentration of S2 minus that's remaining in the solution. That's wrong, right? Because what you are finding here is not the sulfur ions that's remaining in the solution, but the concentration of S2 minus that has been precipitated. Okay, so please note. Alright, so for part 3 of this question, in a beaker, it is found to have a mixture of both Fe2 plus ions and aluminium ions found in the lab. So they ask you to suggest how the separation of these two aqueous ions can be effectively done. Carried out. And using the equilibrium concepts to explain your observations and include any relevant equations in your answer. So your thought process should be this. Which reagent should I add in order to separate these two ions? Okay, preferably one should be a precipitate while the other one remains in the solution so that you can separate these two ions out. And furthermore, in the question, they ask you to use equilibrium concepts. Please be very clear. We are looking at Le Chatelet's principle, POE shifting, to explain the observations. So what you can add is actually equals any OH until in excess to both solutions. And this is not something new to all of you. Okay, you have learned this in QA to separate two cations. Okay, the most simplest way is to add excess of any OH. Alright, it's a big hint to you guys already. This is a QA question in a theory paper. Okay, white PPT of aluminium hydroxide forms, it dissolves in excess of any OH because it's amphoteric to form a colorless solution, while the green PPT of iron 2 hydroxide remains insoluble. Okay, so we have answered the first part to talk about suggesting how the separation of the two aqueous ions can be effectively carried out. Then how do you use the equilibrium concepts then? Right? So based on your theory, when you should have this first equation, aluminium hydroxide is a sparingly soluble salt with its ions, Al3 plus as well as 3 OH minus. This is equation 1. But when excess of OH minus is added, a complex formation takes place. So equation 2 is the one that warrants a tick. Okay, with excess of OH minus, it will form the complex AlOH4 minus. And this addition of excess of OH minus, it will shift the POE of equation 1 to the right. Alright, causing the precipitate to dissolve. This is the one that I'm looking for. Okay, I repeat again. So once you have excess of OH minus, it shifts the POE of equilibrium of equation 1 to the right. Therefore, the white PPT gets dissolved and you get a colorless solution. So what are the common mistakes? Some people actually know that you need an excess of OH minus. But when you write the reagent as OH minus, it is actually not a reagent. What is OH minus? It's just telling me that, okay, it's an alkali medium. But what reagent are you using? You need to specifically tell me it's NaOH or KOH. Alright? Many people actually left blank. So this is something that you guys already know and will have known. It's just that you need to practice more of such questions to really approach this sort of questions. Alright? Okay, part D is a periodic table question. Alright, with the reference of the data above, describe and explain the difference in melting points of the elements above. So the thought process should be this, guys. In order to account for a physical property like melting point, we should be using concepts such as structure and bonding, which is part of your chemical bonding. Alright, chapter to explain why is there a difference in melting points of the elements. So a lot of your yes, you point out to me that the first three elements over here, sodium, magnesium, and aluminium, has giant metallic lattice structures. Alright, that will give you a tick. And because of the number of delocalized, this word must come in. If you tell me the number of valence electrons is not good enough, because you need to relate the context back to what you know about metallic lattice structure. That the valence electrons is actually delocalized. Okay, and from sodium, magnesium to aluminium, the number of delocalized valence electrons, it increases. Okay, the cationic charge increase while the cationic radius decrease from sodium to aluminium. Hence, charge density increases. This is also one additional tick. Okay, this information that I have bracketed, it's not in your notes, but I find it to be is actually another point to substantiate why melting point increase. So can you please add on to your notes or your tutorial question this particular point? Let's start it. Okay, charge density increases. Hence, a large amount of energy is required to overcome the stronger electrostatic attraction between the positively charged metal ions and the sea of delocalized valence electrodes. So now this word stronger must come in because it is to compare that from sodium to magnesium to aluminium. You need more energy to overcome stronger. If you just tell me strong, then we are not comparing between these three metals, you see. Okay? So the strength of the metallic bond should come in from this sentence. So stronger is an important word. Okay? Following that, after that, you guys, some of you correctly describe silicon as a giant covalent structure, but many of you didn't receive this tick. Strong covalent bonds. A large amount of energy is required to overcome the strong covalent bonds between Si atoms. You just stop at overcoming strong covalent bonds. And that is wrong. You're got to tell me that we have to notice that the covalent structure itself is between Si and Si atoms, same as diamond. Okay, so this tick is as such. Next, you notice that the melting point actually decreased sharply to phosphorus, and melting point remains low from phosphorus to chlorine. Now, so most of you identified that phosphorus, sulfur, and chlorine, it has a simple covalent structure, and that sulfur exists as S8, phosphorus as P4, chlorine as Cl2. Now, what I'm uncomfortable is that some of you did not recognize that the trend actually goes from phosphorus up to S8 sulfur, then down all the way to Cl. You guys just tell me that, from phosphorus to chlorine, there's an increase in melting point. So please be very careful over here. There's a trend in the melting point that it goes up first from phosphorus to sulfur, then go down all the way to chlorine. And why is that so? Because of the number of electrons in chlorine molecule is actually smaller compared to P4 and compared to S8. Alright? Then therefore you need a stronger IDID. Please spell IDID out. Between the molecules. Again, the word stronger. It tells me the trend. That it increases from chlorine to phosphorus to sulfur. Therefore melting point is strongest, followed by P4 molecules, followed by Cl molecules. So 3 ticks, 1 mark. Total number of ticks, 9 to 10 ticks, it will give you 3 marks. Common mistakes, like I mentioned earlier on. Giant metallic structure. A lot of y'all wrote this. It is giant metallic lattice structure. So please include the word lattice. No credit is actually given if you only describe the type of bond. That means once you identify, sodium, magnesium, and aluminum has a giant metallic lattice structure, and it has a strong electrostatic forces of attraction between Why do I not give you credit for the description of the type of bond? Because you did not compare the strength between the elements. Okay, you have to tell me the trend. Okay, from sodium to magnesium to aluminium. Why is it increasing in terms of the strength? Some of you identified a lot of wrong trends, like I mentioned. IDID strength increases from P to S to Cl. No. And many of you did not indicate the trends clearly. So you have to be able to write proper sentences like that. Increase in the number of electrons from chlorine to phosphorus to S8. Okay, so please take note. Okay, and finally for this part of the question, I think I'll just talk about the common mistakes. So for this, a lot of you guys actually identify element Y as SiO2. Okay, it is an element. So what I'm really looking for is silicon Si. That will give you 1 mark. And some people actually identify aluminium oxide as this particular oxide. But bear in mind that aluminium oxide is actually amphoteric in nature. It reacts with both acid and base, so it cannot be the Y. Okay, so please go and memorize periodic table. Okay, it will be useful for your upcoming A levels. Okay, how do you write the equation and what is the eventual pH of the system? Okay, that's all for question 4.